All right, let's talk about something that is absolutely fundamental to engineering. How do you make sure that a part designed in one country can fit perfectly with another part made halfway across the world? Well, you need a universal language. And today we're going to learn that language. It's called Geometric Dimensioning and Tolerancing, or GD&T for short. It's really the invisible set of rules that makes our entire modern world fit together.
Okay, so let's really dive into this. Picture this. You're building a high-performance engine. The engine block is being machined in Germany, and the pistons are being made in Japan. How do you guarantee, with absolute 100% certainty, that every single piston is going to slide perfectly into every single engine block? Because if you're off by even a fraction of a millimeter, that could mean total catastrophic failure. This is the exact high-stakes problem that GD&T was invented to solve.
So, on the left, you're looking at the old way of doing things. It's called plus or minus tolerancing. And it basically says, hey, this part should be about 10 millimeters, give or take a little bit. The problem is, how you measure that little bit might be different from how I measure it. It's subjective. But now look at the drawing on the right. That's GD&T, and it's a whole different ballgame. It is not a suggestion. It is an ironclad contract. It's a set of crystal clear instructions that tells everyone, and I mean everyone, exactly how to make and measure that part, leaving zero room for mistakes. To really get why this is such a game changer, we kind of have to go back in time. Before we had a universal system like this, manufacturing could be, well, let's just say it was chaotic. Especially when you had different companies trying to make parts for the same product. A tiny misinterpretation of a drawing could snowball into massive assembly problems down the line.
The idea actually started brewing back in the late 1930s, but it was World War II that really lit a fire under it. All of a sudden, you had factories scattered all over the globe, all trying to churn out interchangeable parts for things like tanks and planes. And when a wing section made in Canada wouldn't fit a fuselage made in the UK, it wasn't just a small headache, it was a strategic disaster that could literally cost lives. They needed a foolproof system, and they needed it yesterday. GD&T became the answer to all that chaos.
And so, GD&T emerged as this elegant, standardized language. It's a system that uses symbols and rules to describe exactly how a part should be made and inspected. And the goal is to make sure that everyone, from the engineer who designed it, to the machinist who made it, to the inspector who checks it, is on the exact same page.
Okay, so here's the formal textbook definition. But let's be real, that's a mouthful. Let me simplify it. If an engineering drawing is the script for making a part, then GD&T is the grammar and the punctuation. It makes sure the story gets told perfectly, with no confusing sentences. And that ASME Y14.5M standard you see there? That's just the official rulebook that everybody agrees to use, so there are no plot holes in the final product.
Now let's get into the real fundamentals. If we're going to learn this language, we have to start at the beginning. And it's this. Before you can measure anything, you absolutely need a starting point, a universal zero that everyone agrees on. In the world of GD&T, we call this starting point the datum reference frame.
And I cannot stress this enough. This isn't just me saying it. Our sources are crystal clear on this point. The datum reference frame is probably the single most important concept in all of GD&T. Seriously, if you can wrap your head around this one idea, you've basically unlocked the key to the entire system.
So what is it? Just look around you. Find the corner of the room you're in right now. You've got the floor, and you've got two walls that meet at a perfect 90-degree angle. That's it. That's your datum reference frame. It's three perfect planes, an X, a Y, and a Z axis that create a perfect theoretical starting point for every single measurement on a part.
Okay, but here's the really clever part. That corner of the room is perfect and theoretical, but the parts we make are real and imperfect. So how do you lock a real-world part into that perfect corner? You use what's called the 3-2-1 principle, and the best way to get it is to think about putting a book on a bookshelf. First, you lay the book flat on the main shelf. That's your primary datum. It needs at least 3 points of contact so it doesn't rock. Then you slide it back until it touches the back wall. That's your secondary datum, making contact in at least 2 spots. And finally, you nudge it against the side of the bookshelf. That's your tertiary datum, one last point of contact. And boom, the book is completely locked in. Everyone can now agree on its exact location. All right, so we've built our stable foundation. We have our bookshelf corner, our datum reference frame. We all agree on where 0 is. So now what? Now we have to actually write the instructions. And for that, we use something called the feature control frame. This little rectangle right here, this is the workhorse of GD&T. I know, when you first see it, it can look kind of like hieroglyphics. But I promise you, it's just a sentence.
A very logical, very precise sentence. It gives one complete instruction for one specific thing, like controlling the exact position of a hole. So let's decode it together, piece by piece.
Okay, so the very first box tells you the what. This symbol tells you what geometric rule we're applying. Are we trying to control how flat a surface is, or the precise location of a hole? Or maybe we want to make sure two surfaces are perfectly perpendicular. This symbol is the verb. It's the main action of our instruction.
The next part of the frame tells you how much. This number is your tolerance. It basically defines your acceptable wiggle room. It's the total amount of variation that's allowed for that feature. It tells you exactly how strict the rule from that first box has to be.
And finally, the last boxes tell us where from. You see these letters A, B, and C? That's our datum reference frame. That's our bookshelf corner. These letters tell the inspector, hey, lock the part into that frame we all agreed on, and then measure this feature relative to surfaces A, B, and C. So when you put it all together, you get what to control, how much it can vary, and where to measure from. A complete, totally unambiguous instruction.
So you might be thinking, okay, that's a lot of theory. Why go through all this trouble? Why learn this whole new language of symbols and frames? Well, the answer is simple, because the payoff in the real world of manufacturing and assembly is absolutely massive. When you use GD&T the right way, all the guesswork just vanishes. Your drawings suddenly mean the exact same thing to an engineer in Detroit and a machinist in Shanghai. Inspection becomes a simple checklist, not some subjective art form. And here's the big one. Parts just fit. You get less scrap, less rework, and you stop wasting a ton of time and money on delays. It even lets you save money by using looser tolerances where they don't really matter.
And this really shows you the full potential here. So far, we've just learned the basic grammar, the datums, and the feature control frame. But this table of symbols, this is the entire alphabet of engineering design. Each and every one of these symbols is a specific tool that gives you incredibly precise control over a part's shape, its orientation, or its location.
At the end of the day, learning GD&T isn't just about memorizing a bunch of rules. It's about mastering a language. It is the language that lets you take an idea that's just in your mind and guarantee that it can be built into a physical reality, perfectly, anywhere in the world. We've just handed you the alphabet, so the only question that really matters now is, what are you going to build with it?